Welcome back to Practical PyTorch. In this video, you'll see how a convolution works. It is one small grid of weights dragged across a whole image. We'll build one output pixel by hand, slide the window across the grid, and see why the same weights are reused everywhere. This bright frame is the window. A small grid of weights sits inside it. Drag that little grid over the whole image, one step at a time, and that is a convolution. Everything in this video is that frame moving. This video has 3 parts. First, a kernel is just a small grid of weights, the sliding window. Second, we multiply, add, and write one pixel, then step over and do it again. Third, the weights never change as the window slides. That idea is called weight sharing. Let's start with the kernel itself, a small grid of weights and what its numbers are for. This is a small patch of an image. The left cells are all 2s, so the left side is dark. The right cells are all 8s, so the right side is bright. Where 2 meets 8, the number jumps. That jump is a vertical edge, and finding it is what this video is about. The kernel is a tiny grid of weights. Read the top row from the left, -1. Then 0 in the middle. Then +1 on the right. Every row holds the same 3 weights. This little grid has 2 names, the kernel or the filter. The +1 on the right adds up whatever sits on the right side of the window. The -1 on the left takes away whatever sits on the left. Together, they measure the change from left to right. On flat color, the plus and the minus are equal, so they cancel to 0. The kernel adds up to something only where the numbers change. Lay the kernel over a 3 by 3 patch. Multiply each weight by the number sitting under it, then add up all 9. That gives one number and it goes into one output cell. 9 multiplies, 1 add, 1 output pixel. Now the sliding part. We do that same multiply and add at every position, stepping the window across the image. Start with the window at the top left corner. Every one of the 9 numbers under it is a 2. This patch is flat, all the same color. Now multiply weight by number. -1 times 2 is -2. 0 times 2 is 0. And +1 times 2 is +2. The other 2 rows come out the same, because every row of the kernel is the same. Add the 9 products. -2 and +2 cancel in every row, so the whole thing sums to 0. A flat patch, no edge. Write a 0 into the first output cell, exactly what this kernel was built to do. Now slide the window 1 column to the right. The image does not move at all. Only the frame steps over, onto a new patch of the same picture. That stepping is the slide in convolution. Under the window now, the right column has changed. Those cells used to be 2s, now they are 8s. The window has reached the edge. But the kernel is still the same 9 weights. What moved is the patch, not the weights. Redo the products. The right number under the window is 8 now, so this one becomes +8 instead of +2. Each row adds up to 6. 3 rows of 6 make 18. Write 18 into the second output cell. The edge shows up as a big number. The whole sweep is one line of PyTorch, a single call to conv2d. The output tensor matches the grid we filled in by hand. The first row reads 0, 18, 18, 0 where the color was flat, and 18 at the edge. Do this at every position and the output grid fills in. The left column is all zeros, where the color was flat. The other columns are all 18s, right along the edge. The output is a little picture too, dark where flat, bright at the edge. Now a bigger picture. It is a made-up test pattern, not a real photo. Gray stripes running up and down, with two horizontal bands crossing the middle. Run the same kernel over the whole test pattern. The vertical edges, where the up and down stripes meet, light up bright. The flat areas stay dark, and so do the horizontal bands. This kernel reads left to right change only, so it is a vertical edge detector. One more idea, and it is the important one. As the window slides, the weights never change. These 9 numbers are the kernel's weights. Wherever the window sits, they stay the same 9 numbers. The weights never change as it slides across. So what actually changed between the two positions? Only the 9 numbers under the window, this patch of the picture. The weights in the kernel stayed put. The patch moved, the weights did not. One kernel reused at every position. That is called weight sharing. Count the weights. This kernel has just 9. A dense layer over the same 25 inputs would need 225. Sharing the weights is why a convolution needs so few, and it still knows which pixels are neighbors. Let's pull it together. A kernel is a small grid of weights. Multiply the 9, add them up, write 1 pixel, step over 1 and repeat. The same weights are used at every position. That is weight sharing. It is why a convolution layer stays tiny and still knows the grid. Next, we get the shape right. Your turn. The window steps 1 place to the right. Which 9 numbers change the kernel's weights or the patch under them? Pause and work it out. Okay, here it is. The 9 under it, the patch. The kernel's weights are identical at every position. That is weight sharing, and exactly why a convolution needs so few weights. One question is still open. What size is the output? Stride, padding, and channels decide the output shape, and getting it wrong is the most common CNN error there is. The next video makes it come out right the first time. I'll see you there.